my dear friends. Welcome to my YouTube channel. Myself, Dattu Patel, Assistant Professor from LJIT. Earlier lecture, we are already discussed about the improper integral of type 1 and type 2. Today's session, we are going to discuss about the improper integral of type 3 and comparison test. Let's see. Firstly, type 3. It is definite integral in which one or both the limits of the integration are infinite and integrand becomes infinite at one or more points within or endpoints of the interval of the integration. That means it is a combination of the improper integral of type 1 and type 2. The integral containing the conditions of type 1 and type 2 both, then it is called the type 3 of the improper integral. Let's see one example based on the type 3. Evaluate integral 0 to infinite 1 upon x square dx. Here our function 1 upon x square is a continuous, but whenever we substitute the lower limit 0, then that is becomes infinite, and here upper limit which is also infinite. Means if upper limit which is infinite, that is type 1, and whenever we substitute the interval or the limit in our function, then it is becomes infinite, that is our type 2. Means that is a combination of type 1 and type 2. Here given integral is a improper integrals of the type 3, then upper limit of the integral, that is infinite, and it is unbounded at x equal to 0, which is lower limit. That means here we breaking the limits with the one real number, then I equal to integral 0 to infinite 1 upon x square dx. Then here we consider the any value, any real number. Here I consider the 1, then integral 0 to 1 upon x square dx plus integral 1 to infinite 1 upon x square dx. Means here at position 1 we have to breaking the limit of integration. Now we have to finding the both the integral and both has a finite answer, then it is convergent. If one of them that is infinite, then it is also divergent. Here both the integral convergent means one of them it is divergent, then combination of that means 0 to infinite 1 upon x square dx is automatically divergent. No need to find the I2. Let's see. Firstly we have to finding the I1. Then I1 equal to integral 0 to 1 upon x square dx. Here whenever we substitute the lower limit 0, then our integral become the infinite. Means it is discontinuous at 0 or it is unbounded at 0. Then 0 which is replaced as any constant term which is c. Here I consider this c1. The limit c1 tends to 0. Integral c1 to 1 upon x square dx. The integral of 1 upon x square, that is minus 1 upon x, where x which is varies from c1 to 1. Now limit c1 tends to 0 minus 1 upon x, where c1 to 1. Now applying the upper limit minus lower limit, that will give you limit c1 tends to 0 minus 1 plus 1 upon c1. Now substituting the c1 as a 0, then 1 upon 0, that is infinite, means we get minus 1 plus infinite, then our term becomes infinite. Means I1 which is infinite, then no need to find this second term, it is automatically infinite, or our series becomes divergent. If either it is becomes finite answer, then also our total integral become divergent. Let's see I2. Here actually no need to find the I2, but for the better understanding just I will explain it. Integral 1 to infinite 1 upon x square dx. Here upper limit which is infinite, then which is replaced as a c2. The limit c2 tends to infinite, integral 1 to c2 1 upon x square dx. Then integral of 1 upon x square, that is minus 1 upon x 1 to c2. Then substituting the limits, then limit c2 tends to infinite, minus 1 upon c2 plus 1. Applying c2 as a infinite, then 1 upon infinite, that is 0. Means here 0 plus 1, then our answer becomes 1, which is finite. Here second integral which is finite, but first integral which is infinite, then total integral I equal to I1 plus I2 first infinite, second finite, then infinite plus finite, that is infinite. Means our integral becomes infinite, then it is divergent. Let's see one more example. Test the convergence of the integral 0 to infinite 1 upon x square dx. Here one limit of the which is infinite, means upper limit which is infinite, that is our type 1. Here 0 which is, whenever we substitute the 0 in our function, that it is also becomes infinite, means our function which is discontinuous at x equal to 0, and we can say that it is unbounded at x equal to 0, which is one of the endpoints of the our interval, where close interval 0 to open interval infinite. Means this is the type 3 of the improper integral. For that we have to breaking the limits. Then integral 0 to infinite 1 upon x dx equal to integral 0 to 1 1 upon x dx plus integral 1 to infinite 1 upon x dx. Here we finding the, in first integral that is integral of type 2, and second integral that is the integral of type 1, where we have to finding the I1, that is integral 0 to 1 1 upon x dx. Then here 0 which is replaced as a t, then limit t tends to 0 plus integral t to 1 1 upon x dx equal to limit t tends to 0 plus integral of 1 upon x, that is ln x, where x which is varies from t to 1, then substituting the limits, means upper limit minus lower limit, that means limit t tends to 0 plus ln 1 minus ln t. Now applying the 0, then you all are aware about the values of ln 1, that is obviously 0, then ln 0, that is infinite, that is minus infinite, then minus minus plus, that is our exactly answer which is infinite. Means this interval which is infinite, therefore the total integral 0 to infinite 1 upon x dx is also divergent. Means I1 which is divergent, then no need to find the I2, which is whether it is finite answer or whether it is infinite answer, automatically total integral becomes infinite or it is divergent. Hence integral 0 to infinite 1 upon x dx is also divergent. Let's see next topic, which is p integral. Integral 1 to infinite 1 upon x raised to p dx is convergent if p greater than 1, and it is divergent if p less than or equal to 1. Here it is not necessary each and every condition has a limit 1, but suppose if it is limit a to infinite, then also our condition will be same, means it is convergent if p greater than, and it is divergent if p less than or equal to. Let's see, here we have the basically two conditions, p equal to 1 and p not equal to 1. Firstly we have to discuss about the p equal to 1. If p equal to 1, then our integral becomes integral 1 to infinite 1 upon x dx. Then here upper limit which is infinite, that means limit b tends to infinite integral 1 to b 1 upon x dx. Then limit b tends to infinite integral of 1 upon x, that is ln x, where x which is varies from 1 to b, then substituting the limits, then upper limit minus lower limit, that will give you limit b tends to infinite ln b minus ln 1, values of ln 1 that is 0, then limit b tends to infinite ln b. Now substituting the b as infinite, then ln infinite, that is infinite, values of p that is 1, then our integral becomes infinite, means integral is divergent for p equal to 1. Let's see for the p not equal to 1, then our integral 1 to infinite 1 upon x raised to p dx, then here upper limit which is infinite, then for that replace infinite as a t, means limit t tends to infinite integral 1 to t 1 upon x raised to p dx. You all are aware about the integral of 1 upon x raised to p, that is limit t tends to infinite x raised to minus p plus 1 upon minus p plus 1, where x is varies from 1 to t. Now for the simplified that term and apply the upper limit minus lower limit, that will give you limit t tends to infinite 1 upon 1 minus p inside the bracket 1 upon t raised to p minus 1 minus 1. Here we have the two condition again. p greater than 1 and p less than 1. If p greater than 1, then the t raised to p minus 1 tends to infinite as a substituting the t as a infinite, means t raised to p minus 1 as a infinite, then 1 upon infinite, that is 0, then we have the answer 1 upon 1 minus p into minus 1. That means our answer becomes 1 upon p minus 1, that is, which is a finite answer. Means if p greater than 1, our answer becomes finite, then we can say that given integral is convergent for the p greater than 1. Let's see, for the p less than 1, then the p minus 1 less than 0, and therefore 1 upon t raised to p minus 1, that is written in form of t raised to 1 minus p. Whenever we apply the t as a infinite at that term, then t raised to 1 minus p becomes infinite, means our integral becomes infinite. Then if it is infinite, then we can say that given integral is diverges for p less than 1. So summation n equal to 1 to infinite 1 upon x raised to p is convergent for p greater than 1, and it is divergent for p less than or equal to 1. That means our integral where 1 to infinite 1 upon x raised to p converges for p greater than 1, and it is diverges for the p less than or equal to 1. Let's see next topic, which is direct comparison test. Already we discussed we have the total two comparison tests, which is direct comparison test and limit comparison test. Firstly, we have to discuss the direct comparison test. If we have the two functions f of x and g of x are the two continuous functions for x greater than a, such that 0 less than or equal to f of x less than or equal to g of x, then the integral a to infinite f of x dx is convergent if integral a to infinite g of x dx is convergence, and integral a to infinite f of x dx, which is less than or equal to integral a to infinite g of x dx. If f of x and g of x are two continuous functions for x greater than or equal to a, such that f of x which is greater than or equal to g of x, then integral a to infinite f of x dx is diverges if integral a to infinite g of x dx is diverges. Here we have the total two functions fx and gx. Then for the converges larger function which is g of x, if g of x which is convergence, then automatically f of x which is also convergence, means larger function is convergence, then smaller function which is also convergence. For that similarly f of x which is greater than or equal to g of x, then smaller function which is diverges, then automatically larger function which is also diverges. Let's see one more topic, which is limit comparison test. If f of x and g of x are two continuous functions for x greater than or equal to a, such that f of x greater than 0 and g of x greater than 0, and limit extends to infinite f of x by g of x equal to L, that means which is finite and non-zero term, means 0 less than L less than infinite, means answer must be finite which is in between 0 to infinite, neither 0 nor infinite. Then integral a to infinite f of x dx and integral a to infinite g of x dx both convergence or divergence simultaneously, means either both the functions f of x and g of x are convergence and divergence together. Let's see one example. Test the convergence of the improper integral 1 to infinite cos x upon x square dx. See such kind of example, we have the apply limit comparison test or a direct comparison test. For that upper limit must be infinite, means our improper integral has a type 1, then and then we have to apply comparison test or a direct comparison test or a limit comparison test. Here our f of x equal to cos x upon x square and g of x equal to 1 upon x square. Then you all are aware about the values of cos x which is lies between -1 to 1, means maximum value of cos x, that is 1, means value of cos x which is less than or equal to 1. Now whenever we are substituting the values of x and so on, then obviously cos x upon x square, which is always less than or equal to 1 upon x square for x greater than or equal to 1. So we have to finding the integral of 1 to infinite g of x dx equal to integral 1 to infinite our g of x, that is 1 upon x square dx, and that term which is indicated by the f of x, and this one is indicated by the g of x. Then our integral 1 to infinite 1 upon x square dx. Then here upper limit which is infinite, then limit b tends to infinite, integral 1 to b 1 upon x square dx, and integral of 1 upon x square, that is minus 1 upon x. Then limit b tends to infinite, minus 1 upon x, where x which is varies from 1 to b. Then substituting the limits, that means upper limit minus lower limit, then limit b tends to infinite, minus 1 upon b plus 1. Now replace b as a infinite, then minus 1 upon infinite, that is 0, means 0 plus 1, then answer becomes 1, which is finite. Here we solve the with the help of direct integration method, but suppose we have to use the p integral test, then also it is possible. Then integral 1 to infinite 1 upon x square dx, then here values of p, that is 2, which is greater than 1. Then according to that p integral test, values of p which is greater than 1, then it is convergent. Here our answer will be finite, means integral 1 to infinite 1 upon x square dx is convergent. Then according to the direct comparison test, integral 1 to infinite cos x upon x square, which is also convergent, then our g of x which is convergent, then automatically f of x which is also convergent. Let's see, check out the one more example. Check the convergence of the function integral 4 to infinite 3x plus 5 upon x raised to 4 plus 7 dx. Here our function which is continuous everywhere. Here upper limit which is infinite, that is in form of type 1. If it is type 1 of improper integral, then we apply the comparison test. Here f of x equal to 3x plus 5 upon x raised to 4 plus 7, then we have to find the g of x. Then for the g of x, highest power of numerator portion, that is x, and highest power of x in denominator portion, that is x raised to 4, that is 1 upon x cube, that is exactly g of x. That means dominant term in numerator portion and dominant term in denominator portion, that is ratio of that will give you g of x, means g of x equal to 1 upon x cube. Now with the help of limit comparison test, limit x tends to infinite f of x by g of x, then substituting the values of f of x and g of x, that is limit x tends to 0, limit x tends to infinite 3x plus 5 x raised to 4 plus 7 upon 1 upon x cube, then x cube which is comes in numerator portion, and here in numerator portion x will be common out, in denominator portion x raised to 4 will be common out, and that will give you limit x tends to infinite x 3 plus 5 by x into x cube upon x raised to 4 which is common out, then 1 plus 7 by x raised to 4. Here x raised to 4 will be cancel out, and remaining term becomes limit x tends to infinite 3 plus 5 by x upon 1 plus 7 by x raised to 4. Now substituting the x as an infinite, that means 3 plus 0 upon 1 plus 0, that is 3, which is finite and non-zero. For that we have to finding the integral 4 to infinite g of x dx, because whenever we apply the limit comparison test, either both the integral are convergent or divergent together, then we have to finding the convergence or divergence of the g of x, that is integral 4 to infinite 1 upon x cube dx. Then here upper limit which is infinite, then which is replaced as a b, the limit b tends to infinite, integral 4 to b 1 upon x cube dx, then integral of 1 upon x cube, that is minus 1 upon 2x square, where x which is running from 4 to b, then substituting the limits, then limit b tends to infinite minus 1 upon 2b square plus 1 upon 32, applying the b as a infinite, then 1 upon infinite, that is 0, means 0 plus 1 by 32, that is 1 by 32, which is finite. Here we can also apply for the integral test, p integral, which is 4 to infinite 1 upon x raised to 3 dx, means here values of p which is 3, which is greater than or equal to 1. Here limit has any value, but condition will be same. If p which is less than 1, then it is divergent. Where p which is less than or equal to 1, then it is divergent, and p which is greater than 1, then it is convergent. Here limit which is greater than 1, then it is convergent according to the p integral test. Here integral will be 1 to infinite, 2 to infinite, 4 to infinite, but condition will be same. That according to the p integral test or a direct integral, we can find our g of x which is convergent. If g of x is convergent, then automatically f of x which is convergent, means both the integral either convergent or divergent together. Hence, by the limit comparison test, integral fall to infinite 3x plus 5 upon x is 4 plus 7 dx is convergent. Let's see, check out the one more example. Test the convergence of the integral 1 to infinite e raised to minus x square dx. Here e raised to minus x square is a continuous function, means on the interval open in close interval 1 to infinite. Since x square which is greater than or equal to x, obviously whenever we substitute the any values of x, that x square which is greater than or equal to x, then multiplying both sides with minus 1, that implies minus x square which is obviously less than or equal to minus x, then applying the exponential form, then e raised to minus x square which is less than or equal to e raised to minus x. But integral 1 to infinite e raised to minus x dx equal to limit t tends to infinite integral 1 to t e raised to minus x dx. Here that is the improper integral of type 1, that infinite which is replaced as a t and limit t tends to infinite. You all are aware about the integral of e raised to minus x, that is minus e raised to minus x, where x which is running from 1 to t, then substituting the limits upper limit minus lower limit, that will give you limit t tends to infinite e raised to minus 1 minus e raised to minus t, then t as a infinite, that will give you e raised to minus 1, that means 1 upon e, which is finite answer, means or normal values of e, that is 2.71a. Therefore our integral 1 to infinite e raised to minus x dx is convergent. So the according to the comparison test, integral 1 to infinite e raised to minus x square dx is also convergent. This is all about the topics of the improper integral of type 3 and comparison test and direct comparison test, limit comparison test and p integral. I hope you guys learn something from this video. If you like this video, then thumbs up. If you think that this video will help some of your friends, then do the share with them. If you want to watch more tutorial like this, then you can subscribe my YouTube channel, and whenever I upload the new video, you get the notification. If you have any query regarding this, then feel free contact me. Thank you so much for watching me.